Alright, today we're going to be talking about continuity in behavior and limits of functions. So right now, everybody should have their calculator ready to go. Very first thing I'd like you to do in your calculator is carefully type this function in. And we're going to evaluate whether the function is continuous or discontinuous at this particular point right here. So go and type a negative. You can hit alpha y equals enter. Type in a 2. Go down, a 3, an x, and we're going to square it. Okay? Now, what I'd like to do is just hit the graph button, take a look at that graph. I didn't put any grid lines or anything on the graphing calculator, but there is the picture of your rational function right there. So what I'd like you to do is to take this graph and just make a little sketch of it on your paper. So right now, just draw a little x-axis and the y-axis. And make a small sketch. Look at your calculator and you'll see your graph. Looks something similar. Oops, sorry. This right here. Okay. The y-axis right here. The y-axis where x is equal to 0. That represents an asymptote. There is an asymptote at x equals 0. Now, at the point x equals 0, there is discontinuity in the graph. What type of discontinuity is happening in this particular picture? Yes. Oh.
Infinite.
It is infinite discontinuity. What I want you to write, listen. Infinite discontinuity at x equals 0. And a lot of times when I think about electricity, okay? Like the flow of electricity. We know when there's a flow of electricity because we have our lights on. As soon as that flow stops, if it becomes discontinuous somewhere in our house loses power, we know that electricity is no longer what? Continuous. It's now discontinuous. So right here, let's follow. Let's pretend like this right here represents the flow of electricity. Okay? So, right here, we were asked to evaluate it where? At x equals a -1, right? So right here, at where x is a -1, is right in this particular area of the graph. So is it continuous right there at that point? It is, right? But where's the only place it's not continuous? It's not continuous where x is equal to 0. Okay? So, the answer to number 1 is yes, it is actually continuous. It is continuous at x equals a -1. It's just not continuous where x is equal to 0. Alright? So, if I were to go, to this problem right here, okay? At x equals -1, it is continuous. But if I were to change this part right here and say, is it continuous at x equals 0? Then your answer would be no, it's not. It has infinite discontinuity. So you have to evaluate it wherever the point is, whether it's continuous or discontinuous. So right now, definitely continuous right there. It's just not continuous right here. All right, moving on to problem number 2. All right. First thing I'd like us to do is I'd like us to type this in the calculator. Alright? So y equals, we're going to clear this out. Alpha y equals enter. In the numerator, x minus a 2. In the denominator, we're going to put x plus a 4. And then we're going to graph it and take a look at this graph. Now I'm going to draw some things in that you may not realize are there. So right here, right here, at a -4, there is an asymptote right there at x equals a negative 4. They're also right here at a positive 1 on the y-axis. We actually have a horizontal asymptote running this direction in this problem. So we put y equals 1. In parentheses, we put h dot a, not for half, but for horizontal asymptote. We put v, a, that's a vertical asymptote right there. So I want you to make a little sketch of this on the paper. Okay? And then we're going to evaluate. Is f of x, which is this rational function right here. Now, quick review. The reason why we have a horizontal asymptote at y equals 1 is because these have the same power, and that coefficient is a 1, and that coefficient is a 1, and 1 divided by 1 is 1. So that's a way to check for horizontal asymptotes. If this up here, this binomial has the same power or degree as this binomial, you can divide the coefficients in front of these variables. So if this was a 2 and this was a 1, then your horizontal asymptote would be right up here at y equals 2. That's a quick review. We don't have to worry about that. Right now, we just have to evaluate where this is what? Is it continuous or discontinuous where? At x equals a negative 4. So if we were to plug in a negative 4 right here, what's going to happen to this denominator right here? It's going to equal 0, right? And so anytime you make a denominator equal to 0, that's so that's where this vertical asymptote right here is created. So do we have continuity or discontinuity? Discontinuity. What type? Infinite. So what you're going to write on your paper is you have infinite discontinuity at x equals a negative 4. And that's your final answer for that second problem. What if I said, do we have continuity when x is equal to the number 5? 1, 2, 3, 4, 5. Do we have continuity right there? Yes, we do. Because you see the graph going through that point from either side. It's going to the exact same point. So it would be continuous at x equals 5. There's only one place where it's not continuous. The only one place is right here where that vertical asymptote is located. Now, let me show you how you guys can find whether it's infinite discontinuity without looking at the graph. Go to your calculators, if you would, please. Go to your calculators. And I want you guys to hit second window and change it to ask. And we're going to look at numbers really close to the number of negative 4. So after you go to ask, it's second graph, and we're going to ask our calculator, what would the value be at a point on either side of negative 4? So think about it this way. Think of a number line, since I'm talking here, and you're not, it's kind of hard to hear, kind of hard to see. So let's say on a number line, we're at a negative 4. What would be, not a negative 3, but what could be a really close number right there to negative 4?
Negative 3.9.
Yeah, like negative 3.9. And how about right here, just on the other side, not a negative 5, but right here on the other side, what could it be?
Negative 4.9.
Negative 4.1. So what I want us to do is I want to see what's happening. Is it getting close to the same point or really far away? So what we're going to do right now is we're going to type in a negative 3.9 and press enter. And then we're going to type in a negative 4.1 and press enter. Wow, these numbers right here are not what? They're definitely not close. One of them is going a negative direction, and one of them is going a positive direction, which kind of makes sense if you look at the graph. Look, negative 3.9 is going where? It's going down. Negative 4.1 is going up. That's that's where the infinite discontinuity is happening. All right, going in complete opposite direction. All right. All right, our next problem is x cubed minus 2x plus 2. If we hit the graph, we have the graph right there. All right, and we are supposed to evaluate whether f of x, which is x cubed minus 2x plus 2, is continuous where? At x equals a 1. So x equals 1 is right here. All right, let's just check. If I'm tracing this, right? If I'm tracing this, and I'm going towards this point, does my pencil ever leave the paper through that point? No. So if it never leaves, and if you never have to lift your pencil or pen as you're tracing it, that lets you know what? That lets you know it is continuous. It's continuously going through this point at x equals 1. There's no jump or discontinuity in your graph.
So it's continuous.
No, it's just continuous. If it's continuous, it's just continuous. What type of discontinuity is there? There's 3 different types, right? There's infinite discontinuity, there's jump discontinuity, and hold on, I'll go back to my let's see here. Where are my pages? There. Let's look right here. We'll go back so you guys can see this real quick. All right? That's continuity test. All right. Let's see here. Go down. Right here. Take a screenshot of this. Here we go. Here's a screenshot. We have infinite discontinuity right here. There's that vertical asymptote. Here we have jump discontinuity because as you're going down this graph, before you can continue to go, what do you got to do? You got to jump up. And then this is called removable discontinuity because as you are going towards the value of c, which is right here, guess what happens? There's a hole in the graph. So that right there, any type of point discontinuity is called removable discontinuity. So you're continuous all the way up to that point. So it says right here, it's continuous everywhere except for this little tiny value. So those are the 3 types of discontinuity. All right? Let me go back to this one. Here we go. What I want you guys to do right now is type this one in. If y equals, this is problem number 4. Alpha, y equals, enter. In the numerator, we have x plus 1. In the denominator, we have x squared plus a 3x plus a 2. I want you to hit graph. Take a look at it. All right. So right now, what we're going to do is I'm going to take a look at this particular graph. Right here, it looks like I have a vertical asymptote right there. So I'm going to rewrite my function. The asymptote? No, it should be straight up and down. So, okay, if mine's a little bit off, I apologize. All right? It's okay, all right, I'll fix it.
It kind of looks curved.
I apologize. I'll try to make it straight up and down.
No, it just kind of looks curved.
Well, okay, well, you can sit in front of me, right over here. All right. So yes, asymptotes, verticals are going straight up and down. Right here, this asymptote is at x equals a negative 2. What are the 2 points we're supposed to evaluate? Negative 1 and negative 2. So we're supposed to evaluate it at negative 2, and then we're supposed to evaluate it at a negative 1. So, negative 2, there definitely is what? Problems. Discontinuity, right? What type? Infinite. Of the infinite variety. I don't feel like rewriting it. So this right here There's discontinuity that is happening that is infinite. X equals a negative 1. So if we were to go to our table and check at negative 1, ooh, what do you get? Error. Huh. Wait a second, what do we get negative 2? Error. Well, every time you see an error, is that always going to be infinite discontinuity, or could there be another possible type of discontinuity? Okay, how about this? Do you see anything jumping? So let me show you something. Algebraically, let me show you something. This bottom denominator right here, this trinomial actually is factorable. What does x squared plus 3x plus 2 factor to? Then it factors to x plus 2 and x plus 1. That's right, Bailey. Now, this one right here, negative 2 plus 2 gets you to 0. This one right here, negative 1 plus 1 gets you to 0. But watch this. Does everybody see how there's an x plus 1 in the numerator and there's an x plus 1 in the denominator? So those can cancel each other out. What do you guys remember from last year? That creates in the graph. Whenever you can cancel out a binomial, yes. A binomial here cancels out this binomial. Guess what we just found? We just found a hole at x equals a negative 1. So whenever there's a hole, what type of discontinuity is there when there is a hole? No! No? What? Yes, removable. It is called point discontinuity, but we call it removable discontinuity. So right here, you're going to write, there is removable discontinuity, which is point discontinuity. You're right. Okay? Just going to put the word point because it's happening at a point where? At x equals a negative 1. So how many types of discontinuities do we have going on here? We've got 2 different types in the same problem. Now, how can I represent that in a drawing? I said, please represent this in a drawing. At negative 1, right here. You see where x is a negative 1 right there? What I want you to do is go down here in your paper, just put a little hole in your graph right there. Okay, so yeah, negative. Yeah, when x. I apologize. Yeah, I was wrong. Sorry. Negative 1 is right here. Good job catching me there. No been bad. No been bad. My apologies. So right here at negative 1. Yeah, put it. Put it right here. Oh, Control Shift. What's going on right here? Try that. Nope.
This is all moved.
I would say it's on the pattern.